Hello everyone, welcome to our 15th R&D session. I'm Monica Fernandes from EDP New. EDP New is a R&D center of EDP, and we have been organizing these R&D sessions since last year. Actually, today we are celebrating 1 year because we started in June of last year, and since then we have been organizing different webinars in different topics that we have been working on in our projects. And in case you didn't have the opportunity to watch these past sessions, you can go to our website where we have all these sessions recorded. Today's session will be about floating of offshore wind. And we plan a very nice session with a panel of experts in the topic that will help us on understanding better this sector. And feel free to ask your questions in the Q&A chat. In the end, we'll have some time to answer to your questions. And without further ado, I would like to pass the screen to my colleague João Formiga, which will lead this session. And I wish you all a great session. Thank you.
Well, thank you, Monica, and welcome back, everyone. Good afternoon. Thank you for joining to this exciting R&D session, where we will shed some lights to the floating offshore wind industry. So today, as Monica mentioned, we will have 3 distinguished guests. From Ocean Winds, we will have Tiago Duarte that will present this recently created joint venture between EDP and ENGIE. Then from Principal Power, we will have Clara Santos, bringing and presenting Principal Power, the floating offshore wind true pioneers that brought to us the wind float technology. And then we will have Alex Raventus from X1 Wind presenting the disruptive floating wind system that is being materialized in Pivot Point project, a project in which EDP New proudly makes part of. We will finish as usual with a roundtable and the session of Q&A. So please pose your questions throughout the session. But before leaving the word to the experts, I would like just to provide you a brief context of this floating offshore wind industry. So we all know that offshore wind, and especially the bottom fixed offshore wind, is playing a pivotal role in the electrical decarbonization. And the recent studies stress this preeminent challenge that offshore wind is tackling with the electrical decarbonization. In fact, Wind Europe recently shared or claimed that in the last year, in 2020, around 26.3 billion Europe were invested in the offshore wind industry, establishing a new investment record in the European Union, and to accommodate the deployment of around 7.1 gigawatts that will be deployed in the next years. Moreover, in this study, it is also mentioned that it's likely that until 2030, we will have more than 205 gigawatts of installed capacity of offshore wind. We also know that both onshore and offshore wind are playing an even more important role when it comes to the energy mix, and it is estimated that by 2050, around 1/3 of the electricity needs will be fulfilled by both onshore and offshore wind. Just to wrap up these numbers on the offshore wind industry, we know as of today that for the next 5 years, we have already in the pipeline around 150 new offshore wind projects that are scheduled to be operating in these 5 years. But as this offshore wind is gaining momentum, we would like to emphasize the role that floating offshore wind is having nowadays, holding the key, we believe, holding the key to reach the net zero emissions by 2050. And this is easy to understand why. So we know that around 80% of the strongest winds are in waters whose depth is around 50 to 60 meters. Obviously, this depends. In the US is around 60%, Europe 80%, but overall speaking, worldwide, we have these numbers. And we know that for these particular locations, we have a more abundant and consistent wind, which is great, especially when combining with taller wind turbines, we will have a higher capacity factor. And we know that there's a lot of uncertainty still, depending on the political governance, depending on the industrialization and the commercialization. But some figures, some recent figures point out that with the commercialization of the floating offshore wind, we could achieve up to a reduction of up to 65% in the level of levelized cost of energy over the next decade, and with this having around 10 gigawatts of installed capacity by 2030. Moving on now to the technological side. We know that this industry is learning a lot with the bottom fixed offshore wind, but we need to stress that the oil and gas industry has inspired most of the offshore wind floater designs. We know that the floating wind turbines are moored to the seabed with multiple mooring lines and anchors in much the same way that a floating oil platform is moored to the seabed. And here in the image on the left, we can see the foremost common floating or floaters that we have in the market, or at least the ones that have more momentum. So we know that barge and semi-submersible floaters sorry, rely on the buoyancy to provide its stability. Then we have the spar, and for instance, Equinor has been using the spar buoy in the high wind projects. And we know that this sort of technology relies on the gravity to provide the stability. And then we have the tension leg platform that relies on the tension in the mooring system to provide the stability. Obviously, I'm leaving this in an over simplified way, but at least for the semi-submersible and for the tension leg platform, we will hear a bit more in detail from Principal Power and X1 Wind for the tension leg platform. Wrapping up, we know that the industry is facing huge developments. So we have around 30 concepts that are being developed worldwide, but we know also that this is a certainty because we have nowadays around 15 units current online and producing energy. And lastly, I would like to leave an important fact that the floating offshore wind actually, in terms of environmental impact, is much less invasive to the seabed activity when in comparison to the fixed bottom offshore wind, both throughout the installation, but also during operation. Having said this, and without further ado, I would like to leave the word to the experts. And now I would invite Tiago Duarte. Tiago is the head of floating wind on the corporate technical team of Ocean Winds. He joined Ocean Winds in December 2020 after supporting EDP Renewables in the floating wind projects, namely WindFloat 1 prototype and WindFloat Atlantic. And Tiago holds a master's degree in mechanical engineering. He has been working in this industry for the last 10 years, and I'm sure that he has a lot to share with us. Tiago, please, the screen is yours.
Thank you very much, João. Good afternoon, everyone, and thank you for the attending this session today. I believe you can see my screen already, so I will progress. Presenting you OW, Ocean Winds, and talking a little bit about our projects and our objectives. So it seems I'm having some technical issues. Can you still hear me?
Yes, Tiago.
Okay.
Yeah, now we are seeing.
Okay, sorry about that. I don't know what happened there, but it froze for a second there. So Ocean Winds is a joint venture between Energy and EDP Renewables. These two companies were already working together in several offshore wind projects, so it came very naturally that they joined forces to create some critical mass and really become a relevant player in this industry. The ambition is high for us, and so are the targets that I will highlight in the next slides. Here you see a bit the key factors from OW, or the key fact sheets from OW. It's the sole investment vehicle for both EDPR and Energy to invest in offshore wind projects. Both partners have contributed with their current stakes on the existing projects as initial assets for the company, and also with the participation to the current pipeline of the company. We have quite ambitious growth targets, and I'll go over that in more detail in the next slides. But OW is in the end jointly controlled by both companies with a fully integrated team, both from technical, procurement, financial, all the other support areas, and headquarters in Madrid. So we have most of our team members there, and also offices located around the world according to the locations of our projects. This is probably the most interesting part of my presentation, and you can see on this slide our current portfolio of ongoing projects. We have currently under operation Windfloat Atlantic and CMAID already installed and the final commissioning, and also Mora East, which already started producing energy and is under final stages of construction and commissioning as well. Out of this portfolio, you can see that already 25% of this are floating wind projects. So in reality, floating wind already represents a significant stake in our portfolio, and it will increase going forward. Just to highlight these projects in France, which will be the next challenge for us, reaching FID still this year, will be EFGL. It's a 30 megawatt pre-commercial project, similar to Windfloat Atlantic, although it already taps into 10 megawatt scale turbines and in the different environment of the Mediterranean waters with different wind and wave resources. The next one would be California with around 150 megawatts of installed capacity in the west coast of the US. And I guess the first big floating project that we are now already in advanced development is Korea Floating Wind with up to 1.5 gigawatts of installed capacity. So these would be the ones that are currently public and we are actively working on. But besides this, Ocean Winds is obviously following up all the developments and the different tenders across Europe, and also some the additional greenfield developments in different geographies. And we can also highlight that from these, there are several ones that are floating wind specific tenders or floating wind development opportunities with key partnerships that actually the technology is opening new markets for us, which is, for instance, the case in Greece, where we have a partnership with the local company Terna that will allow us to explore a new market given the floating wind technology. Besides Europe, we are also quite active in the US and Asia Pacific. In the US, obviously, New York Bight is probably the most active tender right now, but the new administration has announced quite ambitious targets overall for offshore wind. In specific, in the West Coast, we have 4.6 gigawatts of announced capacity, and most of it, of course, will be floating foundations, given the water depths on that region. Also in Asia Pacific, besides Korea, where we are exploring additional opportunities, we also have presence in Japan and China, along with other countries that we are starting to engage with the local authorities and explore opportunities in these areas as well. Ocean Winds obviously is particularly gifted for this market given our past experience, as João Formiga has mentioned already. We were involved since 2009 with the Windfloat 1 prototype that got installed in 2011 and operated for 5 years, and this was a very successful prototype, as everyone recognizes. And also the Windfloat Atlantic project that is currently under operation off the coast of Viana do Castelo, that was installed and finally commissioned last summer, and currently has 25 megawatts, and it's designed to operate for 25 years. So all these lessons learned really make us optimistic that we can gear up with this technology and tackle all these future commercial opportunities for floating wind. Finally, to put some numbers on our target objectives, you see that today we have 1.5 gigawatts already of installed or under construction capacity, with about 4 gigawatts of projects under advanced development. Out of these, again, 25% is already floating projects. But by the end of 2025, we expect to have already 5 to 7 gigawatts under operation or final construction, which means realizing most of the opportunities that we have now on the table, and also have a project pipeline of between 5 to 10 gigawatts under advanced development. All of this paving the way to a greener future, obviously, and with very selective investment criteria established by our shareholders. So in conclusions, OW benefits from a quite unique starting point, and in particular in floating wind, we have quite a unique background, and we're really keen to further develop the first true commercial projects in floating wind in the coming years. So I'll leave it at that, and I think we'll have very interesting discussions later on today as well.
Thank you, Tiago. Very, very interesting and enlightening presentation for sure. And as you mentioned, we will have time for an interesting discussion, but it was great to get to know these numbers from Ocean Winds. And despite being a newborner, it is great to see what you have achieved so far as well. Now moving on and leaving to the technological partners, or the ones that are the developers. We will have now Clara Moura presenting Principal Power and its concept that is well known from everyone. Clara serves as Principal Power's commercial and strategy manager, where she contributes to the definition of business and market strategy. For the past 10 years, Clara has developed her career within the energy sector, with further experience in oil and gas and renewable industry, namely in the offshore wind industry. Clara holds an MBA from Porto Business School and a master's degree in civil engineering from PhilP. And I believe that Clara will now have some very interesting highlights for us regarding Principal Power. Clara, please.
Thank you. Can you hear me? I'm not sure I've unmuted myself.
Yeah, perfect.
No, I unmuted myself. That's good. Thank you so much for this, João, and for the invite to be here today. It's always a true pleasure to sit here with you and discuss something that it's so dear to us here.
I believe we lost you, Clara.
Hello, can you hear me?
Yeah, we can hear you.
Sorry.
For a bit.
I'm definitely struggling here a little bit. Let's see if, okay, I think I'm on now. Okay. Moving on to presenting the company. Who is Principal Power and why are we here? Principal Power is a company that was formed in 2007 to serve the deepwater wind market. We have grown roughly to 100 people as of today and have our headquarters in the US and pretty much a global footprint. Our principal product is the WindFloat Foundation, floating foundation, first deployed, as Tiago mentioned well, in 2011 and fully proven with 7 years of full operational experience offshore. In 2020, we've completed the commissioning of our full-scale WindFloat Atlantic, as well said by Tiago as well. And really, we are having last year concluded the commission of certainly a project to remember the WindFloat Atlantic, we are currently working with our customers to execute 2 other projects in Europe, and the WindFloat has been adopted as the technology of choice for several gigawatts worth of projects in Europe, the US, and Asia. Starting with a quick statement of context, and João, you already touched on this a little bit, but our company is founded on the belief that floating wind technology is essential to unlocking the full potential of the deep sea. This chart here that you see on my slide shows that the breakdown of wind resources by water depth, with over 80% located in waters deeper than 40 meters. Because floating will enable sponsors the flexibility to select the best sites regardless of the depth or ground conditions, the technology dramatically expands the places where you can build offshore wind, transforming a regional industry into a global one. The implications of competitive commercial scale floating wind are massive, with reduced potential for far exceeds the global energy demands, and with load factors averaging above or something between 40 and 60%. This industry has tremendous potential to contribute to the decarbonization, and that's really why we're in the race, to be able to contribute to it. Look at the long-term potential of floating wind, again already touched upon by João at the beginning, and our projections aren't really that different from there, right? For us, we trust the Carbon Trust Joint Industry Project recently released a report forecasting that the sector grows up to 10 gigawatts by 2030. Really, that's just up there, isn't it? And 70 gigawatts by 2040, with potential to reach as high as 120 gigawatts by later on. And it really, if you start comparing sources and look a little bit at the DNVGL release on their energy transition outlook, you know, they foresee about 250 gigawatts by 2050. So whoever is actually right on their projections, the trend is clearly there no matter where you look. Recognizing that the floating wind technology is now ready, the report concludes still that the speed and scale of this growth is dependent on the conducive policy and regulatory factors that, and further, that good policies create the potential for rapid cost decrease. Most of the near-term capacity is, as you know, it's not a coincidence, expected to happen in places where I've mentioned earlier, we have already or have been working in projects, Europe, Asia, and the US. Moving on to a little bit about our technology. What you see here on my map is on my slide is the WindFloat in yellow, this triangular floating platform with a wind turbine located in one of the 3 columns. I will not spend much time on the features of the solution, but just a hitting on the few highlights that speak to the way that how we help our customers to manage risk. The first one being that it's based on a semi-submersible architecture, right? This is something that has over 6 decades of experience in oil and gas industry. The second one is that we have designed the WindFloat to be compatible with any commercial available offshore wind turbine, right? Only minor software modifications have to be done and potentially some reinforcements of the tower. The ability to use these proven wind turbines within type certified conditions gives our customers the flexibility to both choose the best wind turbine for the project and leverage the long operational track record of fixed bottom offshore wind. And the third, but not less important, is that the system has adjustable draft and is inherently stable. So units can be fully assembled and pre-commissioned in port with onshore cranes and towed to site where they are connected to conventional pre-installed mooring systems. Somewhat obviously, onshore construction, which is what we do with the WindFloat, is both low cost and low risk when compared to offshore, of course. Our approach to commercialization of the technology has always recognized the importance of taking steps by steps in order to well manage the risk. The story, and I'm not going to go back to this, Tiago already did, the story really started with the WindFloat 1 prototype that we had deployed off the coast of Portugal with the 2 megawatts turbine. This was really the beginning. Just another hint on that is that after completing that project, or after fully proving the technology, we were able to complete a life extension for our client Cobra Wind, supporting the deployment of that same structure at the Kincardine project in Scotland. As of today, we are currently supporting our clients with other projects in Europe, namely the French project, as Tiago mentioned, and also the Kincardine project, which will, as soon as it's fully commissioned offshore, which is due to happen really in the next months, will become the world's largest floating offshore wind farm. These small arrays have allowed us to prove economics, refine execution plans, and develop an operational track record that at all contributes to readiness for industrial scale applications. The WindFloat project, as well as the Kincardine and EFGL, have been fundamental to prove two important things to this point. The technology is performing well with typical wind turbines, and it's compatible with the available infrastructure at pre-commercial projects level, and that the technology is bankable and suitable for project finance, which is a great KPI. As we at Principal Power turn to the challenge of preparing for commercial projects, we are extremely grateful for the hard-won experience through small arrays like the WindFloat Atlantic shown operating here to the right of the slide. This experience is informing both the WindFloat design and the execution plan choices that we recommend. Now, a few key lessons that we've learned in the meantime around bankability are: number one, empirical data from real-world operations continues to be extremely important to be able to validate and calibrate numerical models. These track records increase the confidence of the sponsors and the financiers while enabling us as designers to have fact-based conversations with class societies about design standards, right, and how to shape them towards floating. Number two lesson is that the coupled dynamics of a floating wind turbine and the metocean environment are complex and should not be underestimated, right? It is therefore important that the project schedule allows suitable time for load interaction between the wind turbine supplier and the floating foundation provider. And this becomes even more important with larger order volumes, where there is more potential for a more collaborative approach to design, which could achieve further optimizations of the coupled system. A likely or a very likely consequence of this is that for floating wind projects, wind turbines may have to be selected earlier as when compared to fixed offshore wind projects. Now, the number three lesson important to highlight here is that supporting various sponsors and contracts throughout several projects has allowed us to gain experience with multiple fabrication methods, ports, infrastructures, vessels, and site conditions, providing important data about what works well and really what doesn't work, right? Because that's the value of track record and lessons learned, isn't it? And this is allowing us to refine everything from the more obvious design and the process choice to our engineering workflow, as well as how we, as designer, structure our commercial offering to assure effective interface. And these fact-based refinements can be incorporated into future project execution plans with confidence, reducing cost and also important, reducing risk. And really, as we continue to successfully deliver on upcoming projects, it is fundamental to keep bringing in the lessons learned in each as we prepare for bigger scale projects and other floating wind applications, such as hydrogen, for example. In this slide, you see a little bit more on detail, a few projects that we have in the UK that will enable exactly this fact. So one, the Kincardine project, the 50 megawatt project with a 9.5 megawatt Vestas V164 in Aberdeen. And without going into a lot of detail, mining my time here, Also like to mention the Dolphin project, which is hydrogen, wind for hydrogen project, which is very important to us, again, proving another application of the technology. And the Erebus project, the 96 megawatt with COD in 2027. Yeah, all of these, in all of these, you either see the different applications or you see the increase in scale, which are fundamental to take floating offshore wind to the next level. Again, Tiago already mentioned well what's up here with this EFGL project, which is so important to us. And so I'm going to move on to my next point in my presentation. So moving beyond the small arrays under execution, we are also supporting several customers with larger projects ranging from 100 to 1,000 megawatts in scale. So based on these engagements, we see a clear path to reach cost competitiveness. The chart here shows that the cost out scenarios moving from small arrays to illustrative first commercial and mature commercial projects, where we have segmented the cost out drivers in 4 categories. First, the weighted average cost of capital, which is a proxy for the cost of financing. The second, the offshore wind sector innovation that the floating sector can leverage, for example, next generations of wind turbine generators. Number 3, wind floating improvements related to the design optimizations and serial production. And the 4th and most important category highlighted here in yellow and responsible really for nearly 40% of the expected cost reduction are economies of scale effects, including larger volume orders, more efficient export systems, and the spread of fixed costs like DevX over more megawatts. As in the fixed industry, where projects are individually between 600 and you name it, 1.5 gigas, and being built in clusters of up to 4 gigawatts, achieving scale is a prerequisite for realizing the full cost reduction potential of floating offshore wind. I've deliberately left timing out of this chart because this largely depends upon the creation of political and regulatory conditions that enable projects to progress. On the topic of larger scale projects, I can highlight projects where we have been involved in the West Coast. You know, some of it Tiago already spoken about on his presentation. The other one worth highlighting is the Progression Energy project in Hawaii for 100 megawatts of project in deeper water depths from 500 to 1,000 meters, and as well another one already mentioned by Tiago in his presentation, the Korea projects. These scale projects will for sure bring a whole level of complexity, right? And we can't just ignore that. But the projects that we have had so far, these the pre-commercial projects that are smaller in scale, those are exactly what have been preparing us for these bigger projects, right? And not that alone, but also the industrialization initiatives and R&D initiatives that we have here in Principal Power, those are for sure important steps that will prepare us for these bigger scale projects in floating offshore wind. To conclude, pre-commercial projects provide again, this indispensable experience and track record to help us succeed in the scalable projects. Scalable projects there are so important to achieve the cost reduction that the industry is claiming. There is a market out there, right? We know the projections are telling us no matter what projections they are, they're there. What we need is that policies and regulatory mechanisms are put in place so that that not only the projects, but also all the stakeholders involved in putting something in the water can develop themselves and prepare for that pipeline. And again, floating offshore wind unlocks a new source of gigawatt scale renewable energy projects globally with high potential to contribute to public and private sector net zero targets, especially when densely populated coastal areas. So we just have to make it happen. And conclude how I started, this is why Principal Power is in business. Thank you so much.
Well, thank you, Clara. A very, very interesting presentation. And thank you for sharing the path you have been walking and the lessons learned while achieving this maturity and while achieving the pre-commercial stage, which I believe all of the stakeholders appreciate these lessons learned. And now moving on to the other side of the spectrum, we have Alex Raventos from X1 Wind, a very exciting project that is now in the deployment stage. And Alex is has an industrial engineering degree from UPC and a postgraduate degree in sustainable energy systems from MIT, Portugal. He has a lot of experience in this industry, having worked since 2007 on several projects related to marine renewable energies, and he has co-founded X1 Wind in 2017. Alex, please tell us more about X1 Wind and the Pivot Point project. You are muted, Alex. Sorry. Still muted. And still loading the presentation. Alex, can you share the presentation, or are you facing some issues? No, I believe we are losing Alex. Alex, if you could please just rejoin again to the meeting. And while we are waiting, I believe we can now look at the...
Yeah. Sorry, Joe, can you hear me now?
Oh, yeah, no, perfect.
Okay, apologies. I just got frozen when I was charging the presentation, but I'm just reloading again. Okay, hopefully it does work this time.
Okay, probably if we just cancel our videos, it will be easy to share.
Can you hear me now?
Yeah. We are sorry for these setbacks. We are facing some technical issues. As I was saying, while Alex is struggling to join, probably we can pick up on the first question we have from the audience. The question is related with the cabling. I believe it's related to the export cables. And the question is related to the fact, or is questioning if cabling is a problem, and if you foresee that there are any issues moving too deeper, or I believe moving further away from shore. Tiago, starting with you, would you care to elaborate on this, please?
Sure. So the floating offshore wind obviously demands that the cable system is slightly different than the fixed bottom ones. We have to employ dynamic cables that accommodate the motions of the floaters. But this is also something that is quite well known from the oil and gas industry, namely the risers that floating offshore platforms have to carry the oil and communications and other systems back to the floating platforms. So we have somehow experience with these cables. The industry also has experience with this. As we go deeper, there might be opportunities for exploring other configurations instead of having the cable on the seabed, potentially having it suspended in mid-water. But technically speaking, there's not a lot of challenge, or at least as showstoppers on this. And just this week we saw, or last week we saw a record being made in Greece with a cable being laid between islands at 1 kilometer water depth, which is, for power cables, it's actually quite a feature this year. So I hope I answered the question, Molos.
Yeah, I believe so, Tiago, and thank you for sharing these insights regarding the cable in Greece. Well, very good to hear that. I'm not sure, Monica, if we have news from Alex. If not, I believe I can pose also, or we can start in parallel the roundtable while we don't have Alex on board. And I would like to start with an additional question regarding the initiative and the mechanisms or the commercialization. Clara, you talked a lot about the policies and the regulatory mechanisms that we need to achieve these figures and numbers. We know that there are a lot of numbers from Wind Europe, from Bloomberg, and other studies, but all of them point out to the fact that this is a growing market, right? But all of them also point out that we still don't have enough incentives or a sharp policy framework that allows the fully commercialization of floating offshore wind. What's your thoughts on this? What do you agree with this vision? Do you think that is something missing in Europe and worldwide?
Yes, João, for sure. And that is a factor that is, in essence, delaying the development of floating offshore wind projects, right? Because we know that the technology there, we know that the technology works. So what we're lacking now is that these bodies start to make not only targets, but that they start. Sorry about this, but that they start to, after creating those targets, that they are able to put the right, correct regulatory framework. What we want to do is really to see a similar trajectory to what we've seen in fixed bottom, right? And there are markets where we see that. We see, for example, the UK moving clearly forward, setting the targets for 1 gigawatt, which it's our opinion is that it's not that impressive, right? So the industry is making an effort to increase that target. But on another note, we see also the US that so far has been quite delayed, sending some clear signals with this new administration and bringing on the 3 gigawatt figures, right? And it is this target setting that will then make the rest of the policymakers and regulatory bodies to the ground to really jointly set out the terms for what will the leases look like and bring them forward.
Okay, yeah, I believe you have covered well what's I don't know, Tiago, if you have something to add to this. Sorry, I just saw your.
No. I'm in agreement with Clara. I think we see obviously that the market is expanding quite quickly in some of these regions where there's already specific tenders and targets for flowing wind, putting a pressure also on the supply chain to be able to meet these fabrication capacities for in some areas. But we also experience some need to educate and develop some frameworks in some countries and some regions where we need to explain a bit more what floating wind is, how is the regulatory frameworks for the environmental and lease areas managed within each geography, which can be quite different from country to country. And thus, this is business development work that we are trying to achieve with our partners as well, and to foster this floating wind potential.
Okay, thank you, Tiago. And on our behalf, on behalf of all of us that are present here, we expect that this business development work is succeeded for sure.
Mm-hmm.
Now we also we have Alex back again on the call.
Joe, can you hear me now?
I can hear you perfectly, loud and clear.
Okay, sorry for that. It just, when I was uploading the presentation, it just got frozen and I could hear you, but you couldn't hear me. I had to restart the computer. This is how it works. Yeah. Sorry for that. Can I present very briefly? I know you're discussing already some of the questions.
Yeah, but please do. I believe it will be important. Yeah.
Okay, very good. So let me know when you can see my screen now.
Yeah, perfect.
Okay. Very good. So yeah, thanks for the invitation. It's a pleasure to be here presenting. With the other members. Both Ocean Winds and Principal Power have been and EDP have been pioneering the floating wind sector for the last decade, and it's a pleasure to be here. Joining you. So at X1 Wind, our background, as you mentioned before, it's also from the wind industry. I started in 2007, and at that time I was working actually in Portugal for a research center, which is EDP is one of part of that research, and that's where the wind float project within Portugal started, and that's where I got very, very much interested in this sector. And then I spent a few years working on wave and tidal, but at the end I understood that floating wind was the future. And that's where everything started. Our goal within the companies, we believe that we've seen the evolution of the wind industry. My business partner and co-founder Carlos Casanovas has been working for Alstom Wind, now General Electric, and Siemens Gamesa for the last decades as well. And we've seen a very linear evolution of the wind industry, right? So we've seen fixed structures on land, which makes sense because you need a tower, which is fixed to the ground, and you need the turbine to rotate, 360 degrees around the tower to orientate against the wind. Then it moved offshore, like the oil and gas did, to shallow waters with fixed structures attached to the seabed. And then again, you need a tower, to allow the system to, the turbine to orientate. But then you go floating, and what we've seen is another linear evolution. Okay, let's put a tower with a turbine on the top of a floater. It does make sense because both are proven technologies, both wind turbines with towers on the top of oil and gas rigs, and both Principal Power and Equinor with the Hywind project have successfully proven the technical viability of those with extremely good capacity factors and very good motions and accelerations, which has helped the sector prove that it's bankable and it's feasible. Now, the challenge of this sector right now is to reduce costs. And not reduce costs. So our objective at X1 is not to reduce costs and compete against other floaters, but I think the whole sector target is to be able to compete versus onshore wind and solar, which have super low energy prices, below 30 euros per megawatt hour in some cases. And this is a huge challenge. So it's not only the good resource that we have there, but the challenge is really to reduce and be competitive, to harvest that resource. And this is where we come from. So at X1, we've developed a disruptive concept in a way that we've thought from the start from a systems engineer. The first question was why allowing and using the tower and fixing the substructure? Why don't we allow the system to weather vane in the same way as a vessel would do with a single point mooring? And therefore, we allow the wind push our structure. Then we no longer need a tower. We can redesign the structure, avoiding the strong bending moments, and make a more efficient structural load transmission down to the seabed. And then also allowing for improved scalability. As turbines are getting larger, we started to see problems in the bending of the blades, and we propose a downing configuration where the blades bend away. Therefore, we can use longer, lighter, cheaper blades, and we can scale up above 15 mil. And last but not least, also a very quick connection system that allows ease of installation with local vessels, and eventually in the future, this could also enable the disconnection and towback port if needed. At the end, so we're trying, and here you're going to see some slides about the pivotal project where EDP NEO is part of, as well as other partners like DMVGL, INTEC-C, and some research centers. And the objective is really to prove this concept and some of the innovations, especially the pivot buoy, which is the single point mooring system, and the TLP connection down to the ground, in order to allow a light design, easy to install, reliable in terms of using only passive systems, but more important of all, it's scalability. So allowing to tap into deeper waters, but also scaling turbines, above 15 megawatts, which is the current target right now. But also quite important is reducing environmental impact. Of course, everything renewables by default, help, combat, tackle climate change. But then by default, there will be some level of impact. In our case, we propose, a TLP mooring, which has a very small footprint on the seabed compared to other systems using catenary lines, but also reducing emissions using less steel for fabricating both the floater and the tower, as well as minimizing, for example, the noise. Instead of using chain, using these steel tendons, which are more rigid and reduce the noise underwater, as well as of other, similar to other floating wind system, will reduce the visual impact and some of other impacts on the economy. So just to talk a bit about the background, I mentioned already, so the company was founded in 2017, so very recent. The concept was developed a few years before that by Carlos at MIT. So he left Alstom because he saw already that floating wind was the solution, and within Alstom there was really no experience in floating structures. So he moved to the US for 2 years, and then he came back and we met working for a company called Blue Water. Then in 2017 we started a company, and we put a very ambitious roadmap within 3 years to put the first operational unit in the water. So we did 2 tank testing campaigns, a lot of simulation work, and then the proof of concept, which you'll see on the next slides. But also above that, then putting a very strong team, bringing the core skills. So experience it with turbine OEMs, which is, critical interfaces to be able to, minimize accelerations, ensuring, the proper operation of wind turbines, as well as combining that with offshore and marine skills with some of our team members coming from companies like Blue Water, Rolls-Royce, Synaptic, and others. And I mentioned before, a very strong technology and R&D background at MIT and other of the top universities. So in the first 2 years of the project, we've done a lot of simulations, both hydrodynamic and couple analysis, as well as CFD, in order to show the benefits of this downwind configuration. Here you can see some studies that we did with Fraunhofer so we've optimized our design in order to minimize the wake after the towers. Since we're proposing a downwind configuration, of course, the towers could produce some level of shadowing after, but we've streamlined this shapes so that we actually have no impact by the fact of using downwind, but we do get the benefits that was mentioned before of reducing the structural weight. And here you can see actually the platform build is going to be installed in the coming weeks at Plocan test site in the Canary Islands with EDP, I was mentioned before, DMVGL, Worley, Plocan, DTU, and other partners. And here you can see an image right now. This is a few weeks ago already, fully assembled, just waiting for the blades to be assembled before commissioning at test. And the next steps is, of course, to jump into pre-commercial arrays. So we've been looking at the strategy from Principal Power, for instance, which we think it was correct to move, from a pilot then to a small pre-commercial array, because for ourselves, which we're introducing a lot of innovation, to jump straight to commercial arrays, it's something that's going to be taking a long time. And we believe, doing an array of 3 to 4 units is the best way forward. And then once our technology has been proven to, to work and be bankable, then we will move into the commercial phase. Thank you very much, and apologies for the technical problems.
Well, thank you, Alex, and thank you for speeding up the presentation. You have put some important issues to be discussed in the table. So if you can, please bear with us just for a couple more minutes to have time for a small discussion and to go through some questions that the audience is actually posing. And starting with you, Alex. Starting with you, Alex. From the developer perspective, the increasing size of the turbines is bringing more challenges to the floating structure design stage. We know that you are still in the phase of testing the pilot, but how do you see this on the long run? How are you tackling this? Are you having into account in your roadmap the increasing size of the turbines? And most important, do you think there's a limit in terms of size and in terms of megawatts? We now see 15 megawatts as the pushing the limits, but please share your thoughts with us.
Yes, well, it's not that we're actually betting on this, future scaling. We've seen the trend. We have already a 12 megawatt unit installed in Rotterdam by G, and prospects of the 14 and 15 megawatt already out there in the coming years. So we believe it's going to be scaling to continue to scale up, and that's why we're betting, on a Darwin configuration, because this enables, a better scalability over time. The wind turbine, the turbine OEMs have been able to scale larger and larger, and put pre-bending on the blades and using carbon fiber to reinforce to avoid what is known as tower strike. But as turbine and blades get longer, this is harder and harder. So putting these turbines in a Darwin configuration, and there's a number of very interesting projects from NREL, for example, that they are looking at 25 megawatt rotors in a Darwin configuration already. As well as Fraunhofer, DTU, some of the leading research centers are looking into that, and that's we believe the way forward for floating wind in particular. This is not so interesting for fixed structures, but for floating wind makes a lot of sense in the long term.
Okay, thanks for sharing this. And Clara, as a technology developer as well, what do you think about this increasing size and being PPI, being the wind float concept not working with downwind? Do you think there's a limit when it comes to the turbine size or to the installed capacity?
Mm-hmm. Well, as the sector moves to industrialization, it is important to recognize that the requirements for commercial projects are very different from the pre-commercials, right? And it is at the commercial stage that we will see these 15 plus coming up, right? Or even 12 plus coming up. To achieve these objectives, the design basis must, from an early stage, holistically consider the full set of requirements at each stage of the project life cycle to assure full compatibility between design choices and the supply chain constraints. And to the specific case of wind turbine generators and how big they can get, this is for sure an important parameter of our industrialization plan. Now, we see that the scale of these new turbines they will have an impact on the platform. I don't think that we see major interface issues with the up to 15 plus, but from there, there might be some changes that we need to integrate, but also we need to have a look at the challenges that the 15 plus or 20 or 25 will bring in the logistics aspects of not only assembling, but also maintaining such turbines, right? You can grow. We know you can grow, right? But you need to remember that you need to transport those up to final assemble sites. So we think there will be a ceiling, and eventually there will be a compromise on what's economically feasible from not only from the construction point of view, but also maintaining, right? What sort of cranes will be able to lift in a cell of a 25 megawatt turbine? Is anyone also thinking about that in parallel as we think about the 25 wind turbines, right? And if you're thinking about maintaining, we see already a lot of room for improvement when you think about maintaining floating offshore wind platforms with the turbine as they are. So when thinking about, okay, what if the turbines, instead of being 10 megawatt, now they are 25? What does that mean for the offshore logistic assets in terms of maintaining? So we know they are growing. but to us, there will be a limit to which they will just have to be a compromise of size versus integration and maintainability of the system as a whole.
Yeah, very, very interesting thought, Clara, and also touches the following question I would like to pose to our key speakers, and before moving on to the other questions that the audience is making, that relates with the supply chain and this ability. There will be cranes with the ability or the capacity to install a 25 megawatts turbine or wind blades. So we know the studies as of today suggest that the majority of the ports are not yet prepared for the let's say the boom of the floating offshore wind, or to bringing floating offshore wind on an industrial case. Now moving or passing the word to Tiago. Tiago, how do you see this possible constraint in terms of the ports? And additionally, there's a multitude of different suppliers to a wind farm, crane supplier, anchor manufacturer, etc. And do you think any of these suppliers can be a bottleneck in the future for the boom of the floating offshore wind?
Well, it's a difficult question to answer because it depends a lot on the project location and the type of structure that we are going to employ. Somehow some of these issues, as Clara mentioned, need to be assessed from an early design basis. And we need to be able to tune our floater design and our floater selection or technology selection, being the floater, but also the turbine, the type of mooring systems and the related marine spread and craneage that is needed to the needs of the project. Some areas might have heavily industrialized naval and oil and gas industries. For instance, Korea is probably one of the best examples of that, with a very big shipyards available there to support this growth, where we can tap in directly to their assembly lines. Some other geographies might not have that chance, and we might have to rely in a different type of marine fleet, for example, or a different type of construction to assemble these units near to the site, or somehow to adapt the design so they can be transported over long distances. So it's hard to say exactly what could be the main bottleneck, and I think Clara touched on a very obvious one, which is the craneage onshore. Just on this specific topic, as we grow the turbine size, there is a clear bottleneck there that I think the fixed bottom offshore industry is now addressing, and we see more and more vessel owners developing and starting construction actually on new builds with increased capacity, both on boom height but also on the weight capacity, to be able to cope with these machines for the fixed bottom industry. And somehow floating wind, by tapping onto onshore cranes, need to accompany that as well. For reference, for example, the crane we use for Windfloat Atlantic, there might be about 40-50 cranes like that around the world, even more potentially. To assemble the prototype that Alex mentioned in Rotterdam, they had to use 2 of those in tandem to lift a nacelle. So as we go to 15 megawatt class turbines, and we're talking about nacelle weights way above 500, 600, maybe 1,000 tons in some direct drive designs, we see that the crane or the onshore cranes that can do this are quite different ones, and we might be talking about ring cranes that there might be 4 or 5 of them in the world. So obviously this poses constraints on the supply chain, and it's something that we are taking into account as we look into our project in the future and the availability of these turbines as we move along to 2030, 2035.
Well, thank you, Tiago. I believe, although being a tough question, you have touched very important and critical points and matters that the floating offshore wind industry needs to face on the long run, at least. Mm-hmm. Now, moving on to some of the questions from the audience before wrapping up. Well, Alex, we have here a specific question. I would say to X1 Wind or to yourself, from Pedro Silva. The question is about the fact of the downwind turbine being or not a limitative factor for X1 Wind, in the sense that the top suppliers are focusing on upwind.
Yeah, no, that's certainly our biggest challenge right now. Is we're going a little bit against the current trend, and this is a bet that we've done in the longer term, is because we see the benefits of scalability, and we've discussed with the top turbine OEMs and the way they do see the benefit of scalability, but these companies at the same time, they have a lot of inertia. And they've been building upwind turbines because it makes sense to have an upwind turbine if you have a tower which is fixed to the ground, because of the shadowing I was mentioning. So in order to convince them, it's a long-term process that we've engaged with them already a while ago. We've actually taken, in our prototype right now, a turbine from Vestas that was proven at Vestas R&D facilities in Denmark, and we've converted in a down configuration to show how easy it is to actually turn it in a downwind configuration. But yeah, that's one of the challenges, is really to in a sector where it's high capex, high risk. In order to make these changes, it takes a while, but we do see some signals from top R&D centers, as well as some smaller turbine OEMs going for offshore downwind turbines as well, that hopefully I think it will cohabit both of them, upwind and downwind turbines, but hopefully we're able to move this forward and try to push the limits.
Yeah. Okay, Alex, thank you. I believe then Pedro touched, let's say, a critical point from your side, but that you are already considering for sure. I believe we still have time for 2 more questions. Let me just bring this one to Clara. Clara, in a few words, do you think that these structures, the floating offshore wind structures and with the wind float structure, can integrate with other bio projects like aquaculture or biohabitat? Do you think this is could be a trend, or could even lower your costs?
Yeah. The short answer is yes, and that is a concern to us. Also, the multi-purpose use of these platforms in the future will bring a lot to the table, right? I think that for now the industry is really focusing on on securing the scaled projects, but once we've mastered the industrialization and we are able to deliver bigger projects in short timelines, that will be the next game, the game of how else can we use this for these platforms for, right? But in the fish pods itself, it's something that we are actually planning, and I'm not sure, Tiago, maybe you can support here as well, planning to do some demonstrations around on the FGL project. We have, at the beginning of the project, installed some sort of buoys where we had some cages with fish, just to demonstrate basically that the habitat is not disrupted by the installation of such technology, which is really a unique initiative and something that we're proud of. And I think that the idea is to bring this now to the actual EFGL project, but something definitely worth to be discussed. I'm not sure, Tiago, if you can add anything on this one.
No, just to confirm your explanation, Clara, indeed, in the FGL project, we're working with the local natural reserve park that basically sits on the coastline and encompasses a part of the marine area around our site. And we have a quite intensive campaign, environmental monitoring campaign, to study the impact of this pre-commercial project, acting as a nurturing for the fish community on site. And so, as you explained very well, we have installed an initial buoy to foster this marine growth. on these cages, and we'll be installing these same cages on our platforms also to monitor the development of these species. So it's really something that we have to work on a project by project basis to ensure that the environmental impact of our projects is positive, or if not neutral. But it is really something that we are taking the next step here in France.
Okay, Tiago, just finishing the questions with you. Also an interesting question that relates to the, as this market is growing and as we move away from the shore, what are the expected new challenge? For instance, the soil conditions, the distance between the turbines, even marine traffic. Will this impact these new locations? Have these additional challenges? What do you think?
Well, this is all these challenges that were mentioned actually are challenges for any project. So on all projects, we need to assess the soil conditions, make sure that we have a suitable soil for mooring, and to select the proper anchoring solution for a specific location. All the regulations need to be there. The distance between turbines is typically driven by the wake effects and how we want to optimize the energy production and minimize turbulent wind to the next turbine that typically increases fatigue loads on the turbine. So as we move further offshore, there's a couple of specific challenges, besides these. One of them is the export cable technology. As we go further and further offshore, we might need to change our typical AC configuration potentially into a high voltage DC configuration that becomes competitive, I believe, around 100 kilometers away from shore, depending on the size of the wind farm. But also our maintenance plan changes significantly. Typically in pre-commercial projects or these initial farms that are located a few 20 kilometers from shore, let's say, CTV or fast crew transfer vessels are typically the way to go. So we go offshore on a daily basis and we come back. If we are in these remote locations where we have these wind farms so far away, we typically cannot have our technicians spend so much time on a vessel going back and forth every day from the wind farm, and thus we have to rely on SOVs, which are basically crew vessels that remain on site and provide accommodation, kind of like hotels, to transfer the workers and the maintenance teams directly to the turbines offshore and remain offshore for typically 2 weeks periods and then rotate from there. So these are probably some of the key differences when we go further and further offshore that we need to take into consideration on our design basis. I think you're in mute, João.
Yeah, you are correct, Tiago. Thank you for specifying these specific challenges as we move away from shore. I believe we are ending or running out of time, so my apologies in advance for not being able to run to all of the questions. But I think we had a very interesting discussion. I would like to thank our guests to share your thoughts and your vision on this exciting new industry, and also thank you for the attendees for being here and to pose all of these pertinent questions that we have. Now, thank you for your time and have a nice evening.
Thank you.
Thank you, João.
Thank you. Bye-bye.
Thank you.
Thank you all. Thank you all. I just wanted to thank to all and also to say that for next month we will have another session in another topic. So stay tuned with us to know the date of the next session. And thank you all. See you next month. Bye bye.